Okay, so today we're going to be covering chapter 1.9, which is going to be what the book calls power functions. We know them as polynomials. Again, it's just review, so you will be okay. Right? So the first thing we're going to do is throw some definitions at you, and then we'll kind of move on from there. So definition 17 is going to be power functions or polynomials in standard form. Okay, it's going to look a little ugly. I will explain it. You will be okay. F of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus da 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 plus a sub 1 x to the 1 plus a sub 0 x to the 0. Okay? And let's put some constraints on this bad boy. 1, a sub n, or actually for all a sub I. So a sub I just means coefficients of x to the I, all right, has to be a real number. Yeah, that's it. 2, x to the I just means x to some exponent I, which has to be a non-negative integer. So examples: 0, 8, ooh, not negative, 57, 4. Non-examples: -1, 1/3, pi, 82 over 50, etc. Okay. What else? Oh, 3, n is your highest exponent, and yeah, that's it. Those are all your constraints. Um, Something to note. Typically, you see this written as a1x. That's just because x to the 1 is equal to x. And 2, you might notice that this is written as a sub 0 because x to the 0 is equal to 1. So a0 x0 is the same as a0 x, or a0 times 1, which is just a0. This is also known as your constant, which you can view as your vertical shift. Should be okay. And then the reason why we want this form is because we have some really nice properties. One, a sub n x to the n is your leading term. For example, f of x is equal to -7x to the 5th plus 18x to the 3rd plus, I don't know, 9x plus -4, right? Your leading term is going to be this guy. 2. Did I clarify the n? Yes, I did. Okay. 2, n is the degree of your polynomial. Yeah, that's it, right? 3 a sub n is your leading coefficient. These two things will tell you some interesting properties about the end behavior of your polynomial. We'll get into that in a second. And something to note, linear functions are polynomials. Okay. So for example, f of x is equal to negative 5x plus 2, right? A sub n, well, actually, let's first identify. N is equal to 1, which means a sub n is equal to negative 5. X to the n is equal to x to the first, right there, right? And a sub 0 is equal to 2, right there. All right, cool. That's it. Um, when we talk about end behavior, we have when n is odd, oops, behavior at, loosely speaking, at, okay? Positive, negative, infinity are different. So if one goes up, the other goes down, and vice versa. If n is even, n behavior is symmetrical, so they either both go down or they both go up. All right. If a sub n is positive, then you have behavior at positive infinity is up, and if it's negative, then behavior at positive infinity is down. Okay. And then when you talk about negative infinity, right, it'll just correspond to that. So a little table for you is, let's see, even, odd, for your degree of polynomial. Oh, yeah, and the degree of your polynomial is this n value. Okay, I don't know if yes, I do. Cool. And then positive, negative for your a sub n. And then we just go like that. If it's even and positive, both sides go up. If it's odd and positive, does this. If it's even and negative, both sides go down. If it's odd and negative, right hand side goes down, left hand side goes up. This is also listed in my notes, just not in this pretty little table. Okay. Okay. Now we're going to make another definition. We're going to call it factored form of a polynomial, which is going to be definition 18. Okay. Factored form of polynomial. Okay. So it's going to look like, it's going to be ugly, but it'll be okay. F of x is equal to a times, and notice how there's no like subscripts here, okay? A times b sub 0 p sub 0 times b sub 1 p sub 1 times b sub n p sub n. Let's break down what these things are. A is going to be your coefficient, and this will behave as leading coefficient as well. We'll explain why in a second. 2, we have b sub I. This just means the ith factor, okay? So like b sub 1 is the first factor, b sub 0 is the first factor, b sub 1 is the second factor. I know, we enumerate at 0, it's silly, I know, I'm sorry, it's CS behavior. B sub I is going to be your irreducible factor, okay? Which means you cannot factor anymore. Okay. Some other gentle insistences is b sub I never equals b sub k, which means we don't write the same factor twice. We just combine the exponents. And I'll explain why that's important in a bit. We also gently insist that this a right here has to be a real number, and it's almost never 0. And I'm going to give you guys a hot second to figure out why that a should almost never be 0. What happens when a is equal to 0 here? Just think about it. Pause if you have to. Okay, I'm going to assume you thought about it. When a is 0, this whole thing is equal to 0. Okay, so I'm going to very gently insist that we don't use a as 0 because there's no need to. Does it work? Yes. Is it still going to be a real polynomial? Also, yes. Like y is equal to 0 is a real polynomial. But gently insist. Okay. What else? Oh, and the last thing, we're going to gently insist that b sub I has no coefficients. So for example, if you have 2x plus 1, right, you could just turn that into 2x plus 1/2. It's still reducible. A good example of a b sub I is x plus 7. You can't factor anything else out, right? Another good example is x squared plus 1, because it's not factorable, at least over the real numbers. Okay, good. Okay, let's see. Why do I bother? Well, what we can do is we can now start talking about the properties of factored form. I know this is going to be a bit faster than my in-person classes, and that's because you guys can pause and run it back. So please do. In my notes, it's going to be called uses, okay? A, like in standard form, is your leading coefficient. So for example, and I'm going to have you guys work this out, okay? So you can convince yourself. F of x is equal to -7, x plus 1, x squared minus 1, right? Look at it. Why, why is it your leading coefficient? What happens when you distribute this out, right? If you were paying attention, you'll realize, oh, that's because this is going to be -7, and then you FOIL this out, x cubed plus who cares, right? This is your highest you can get. You cannot get anything more than x cubed, right? And you can only get x cubed once, right? And that's going to give you -7x cubed plus who cares, right? So that's why that behaves the way it does. 2. If bi, so each of your irreducible factors, is equal to x to the k sub I plus c sub I, right? So this is linear. Ooh, not linear, I'm so sorry. This is irreducible. Again, c is just some real number, right? Then you can say, oh, the degree of f of x is equal to, bear with me now, sigma, which just means the sum of I from 0 to whatever your, what did I say it ended in? N of k sub I times p sub I. Okay? Remember, your k is coming from this, right? It's the exponent that lives in this factor, right? And your p sub I, if you remember, is going to come from this, right? Now, I'm going to give you an example and I'm going to have you work it out so you can convince yourselves, okay? Let's say we have f of x is equal to negative 5 x plus 3 to the fourth, x plus 1, x squared, x minus 3, oops, just kidding, x minus 9 cubed, and x squared plus 19 cubed. Okay, I know these are very big, so I'm going to give you guys a bit of time to do it. Please pause, okay? And if this is a little intimidating, I'm going to show you a smaller example first. Okay, so let's say g of x is equal to 7 x squared plus 1, and then let's say x plus 2 to the first. Let's do squared, right? Big picture, you get 7 x squared plus 1, right? And this guy, do not ever tell me that this is equal to x squared plus 4. That is not true. That is called the freshman's dream, and it is very, very bad. This is not true. Okay, so don't ever tell me that. Instead, this actually foils out to x squared plus 4x plus 4, right? If you notice, this right here gets multiplied down to here, right? Because the exponent here is technically 1. And when you FOIL it out, you get 2, right? And then if you FOIL it again, you're going to end up with something like 7. And then you multiply these two guys together, right? And again, that's the highest exponent you can possibly get. X to the fourth times da 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 da. Or plus da 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 da, right? It doesn't matter what that da 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 is because all their exponents, let's say like this going this way, right? Or this going this way, or even this going here, here, or here, it's always going to be smaller than x to the fourth. So that's why this behaves the way it does. Okay. So I'm going to give you guys a hot second to work this out. Pause, and I'll show you the solutions for this guy. Okay. Okay. So if you're hearing this, you probably already worked it out. And if you didn't, please pause it. All right. So what we're going to do is we're going to say, oh, this formula says the sum of. So we're going to do ki times pi and do it for all 0 to n. All right. All right. This is, let's call this p sub, or sorry, k sub 0. which is equal to 1, because that's the exponent up here, right? The exponent here and your p sub 0 is equal to 4. So 1 times 4 plus here your k sub 1 is equal to 1, and your p sub 1 is equal to 1. 1 times 1, your k sub 2 just happens to be 2. They're not always going to be equal, okay? Equal to 2, and your p sub 2, there's a secret 1 out here, it's going to be 1, so plus 2 times 1. Your k sub 3 is equal to 1. Your p sub 3 also happens to be 3. So it's going to be 1 times 3. And your k sub 4 is going to be 2. And your p sub 4 is going to be 3. So plus 2 times 3. And this is all going to be 4 plus 1 plus 2 plus 3 plus 6. And this is just an arithmetic test at this point if you know how to like add things. This is going to give me 10. This is going to give me 5, so it's 15, and this is going to give me 16. So the degree of f of x is equal to 16, which also means we can very loosely graph this guy. All right, but we'll get back to that because the last important um the last very important detail is going to be details 3 and 4. 3, so property number 3 is each linear factor, so like x to the first plus whatever, each linear factor bi tells us the 0, or a0, I'm so sorry, a 0 of your function. Note if bi is not linear, for example, x squared plus 1, the 0 is imaginary. We don't worry about it. Mhm. And the last fact is each pi of linear, or actually not even of linear, of bi tells us the multiplicity. And in particular, if bi is linear, we can determine the shape of the graph by using pi. I'll explain what that looks like. So, 1, assume that bi is linear. So for example, x plus 7 to the third. This is the linear factor, not the whole thing, just this. Okay, there we go. Okay, so in this example, multiplicity is 3. If our multiplicity is odd, your function passes through your x-axis. So in this case, your function will actually pass through. So if we're looking at this, it'll pass through x equals -7. Okay, and not just boom. If pi is even, your function touches the axis and bounces back. So it'll either behave like this or like this. And it'll depend on what's going on either side. Okay. So what I'm going to have you guys do is go back to this guy and try to graph it. Okay. Um, and we'll go over the solutions together. So give it a pause, and I'll be back. So if you're back here, you probably already worked it out. So let's check our solutions. Okay. So what you're going to want to do is look at the degree, whether it's odd or even, look at your leading coefficient, daddy. Okay. So 1, A is going to be -5. So um, it's going to be down at positive infinity. 2, your degree is 16, which is even, which is symmetrical. So it'll be down at negative infinity as well. Okay, so that's what we glean just from, look at all that. Let's look at the zeros, okay? 3. This is your first factor, okay? X plus 3 has even multiplicity. Even multiplicity because of the 4. Okay, which means it bounces. My personal advice as well is to write this from least to greatest in the sense of um, x equals -3 is going to be furthest from 0, followed by x equals -1, followed by x equals 0, followed by x equals 9. And then once you hit these guys that aren't factorable, you could just leave them at the end. They're not gonna make zeros because the zeros are imaginary. Okay, so don't mind this. Okay, so you have this, you have x plus 1 as odd multiplicity, um, x minus 9 is odd, and x squared plus 19 has no real roots. Okay, so big picture, what you can do is you can say, yes. Am I missing someone? Oh, oops, forgot. X equals 0. X squared, or x minus 0, you can always write it like that. X squared is the same as x minus 0 squared, has even multiplicity, so it also bounces. Okay, so what you can do now is you can say, I don't quite know what happens on the in-between. What I do know is um, this is my end behavior. So on the left-hand side, it should go down. On the right-hand side, it should also go down. Let's see. At x plus 3, even multiplicity, that means that x is equal to -3. It'll come up, and it'll come back down. Okay, here, we finish this. I actually have this out of order, so I should swap them so we can do them in order, but it's okay. X plus 1 is odd. So at x equals -1, it's going to come up, and then it's going to pass through. And then you have x equals 0. That's even, so it's going to go up. It's going to hit 0, and it's going to bounce back up again. So there's the first 0, Second zero. There's zero. Okay. X minus 9 is odd, so at x equals positive 9, it's going to pass right through. And then this, we're not going to worry too much. It's going to wiggle a little bit. It could go up. It'll never hit back here, but it could go up. It could shimmy back down. We don't know, just based off of vibes, right? But we do know it eventually does that and goes right back down. Ain't it beautiful?